Okay, welcome back. Today we have section 1.5, Fundamental Theorem of Arithmetic. And we have an annoying property of division, that it's not true that if A divides BC, it doesn't mean that actually A divided B or C individually at all. For example, we have 4 divides 2 times 2, and of course 4 doesn't divide 2. Anyway, that's that. However, if we add some relatively primeness into the discussion, then we do get this type of property. So here's our first theorem. Number 1, if A divides the product B times C, and A and B are relatively prime, then A divides C. So if A and B share no prime factors, then A divides C. Number 2 is a statement about primes, and it depends on this product notation. So recall this capital Greek pi, the product from 1 to n of a sub I just means successively multiply all these a's together. It's completely analogous to the summation notation that you're probably very familiar with, except instead of adding, you multiply. So you can remember it because that's a Greek pi, which is a p, which stands for product. Anyway, here's number 2. If p is a prime number and p divides a product of ai's, then that's because actually p divided one of the ai's themselves. All right, the proof of this, especially the first one, is our usual linear combination trick with the greatest common divisor. So because A and B are relatively prime, that means we can write 1 as a linear combination of A and B. After that, just multiply both sides by C. And then on the right side here, obviously A divides that term, so it divides that product, ACX. And by hypothesis, A divides BC, so it divides those two terms multiplied together. So since A divides each of these terms, and it's just a linear combination of them, we see that, in fact, C divides, let's see, A divides A, of course, and A divides BC. And therefore, since C is a sum of things that are divisible by A, you have that A divides C, just as we want it. All right, part 2. Of course, the case when there's only one term, that's trivial. There's nothing to say if you look at actually what's going on here. The next step up is the interesting case, and that's the n equals to 2 case. So let's prove this for 2, and then we'll use that to finish off everything with induction. So the setup is P divides A1, A2, because we only have 2 things. Since P is prime, we know its divisors. Let's see here. Are plus or minus 1 in P, so that in turn means that P with essentially anything can only be 1 or the absolute value of P. In particular, this means P with A1 only has 2 possibilities. Either it's 1, and then we can use part 1, that P divides A2, or it's the absolute value of P. And, I mean, at the minimum, this means that P is a common divisor, so P would divide A1. And either way, we're set. Okay, that's n equals to 2. Now the general case. All right, we've already checked our base case. So let's assume it works all the way up to n and check it for n plus 1. All right, so The trick is simply to start with our hypothesis here that p divides this product up to n plus 1. And we're going to write this in two pieces, like this. And since we've already checked the n equals to 2 case, since p is prime, it has to divide one of these two products. All right, well, in the latter case, that's the end of the proof. It divides one of the terms. But in the first case, now we just use our induction hypothesis. All right, so p would divide one of those AIs, and that would be the end of the proof. All right, this will bring us to our first big theorem, and it's the fundamental theorem of arithmetic. You can tell by the name that it's important. All right. Fundamental theorem of arithmetic. For any number, we're going to state this for positive integers. We get the following. All right, the first statement is that every integer can be written as a product of primes. Here the pi's are going to be prime, and we might as well take the mi's to be strictly bigger than 0, or else they don't really contribute. And then the hardest part, I suppose, of this statement is that this expression is unique up to reordering. All right, the proof of this, the first part, is going to be induction on n. The first case is n is equal to 2, and, well, there it is. It's a product of primes. It's 2. So that's done. So we're going to assume the theorem is proven up to n, and then verify that it works for n plus 1. Well, if n plus 1 is prime, then we're done. It's already a prime. Otherwise, if it's not prime, then it factors. So that means n plus 1 can be written as a times b, where a and b are strictly in between 1 and n. However, now a and b, by the induction hypothesis, are themselves products of primes. Each is a product of primes, so their product is still a product of primes. And that'll be the end. All right. So, on to part 2, the uniqueness. All right, in this case, essentially we're going to induct on the sum of the exponents that appear in the prime decomposition. So let's make this definition. S, which is really a function of n here, so sometimes we're going to hide that and just call it S. So we're going to let S initially be all the sum of the exponents, mi, where n is a product of some primes to the mith power. And since we don't know that that's unique yet, we're going to then take the minimum of this expression, which will then give a well-defined definition of S. So add the minimum and we're set. So now we're going to induct on S. And by that, I mean we're going to assume the theorem is true for all n's with an S value at S or lower, and then show it works for the n's where the S value is 1 higher. The base case is when S is equal to 1. Well, if n equals to 1, that simply means that p is prime. Okay, when p is prime, it just doesn't have any factors besides itself, 1, and p up to plus or minus, so it's trivial to check that the theorem works in this case, that it's unique, because you can only write it as itself. I'm going to skip those. They're not really worth it. All right, so some technical difficulties there. Let's see if they worked out. Anyway, so now we'll induct on S, so we're going to assume that things are working for all integers n with up to a certain S value. Okay, so assume the theorem works whenever the sum of the exponents in the minimal case is at most n, and show that it works when it's equal to n plus 1. So let's start with one of those n's where it's equal to n plus 1. So suppose, so that means n can be written as a product of pi to the mi, where the sum of the mi's adds up to n plus 1. And we'll assume this is one of the minimal expressions. Then we'll want to suppose it can be written another way and show that, in fact, it was the same way. So suppose it can also be written this way. Okay, so it's written as a product of p sub i's and a product of q sub i's. We need to show that, in fact, the pi's are the qi's and the mi's are the same as the ni's. Okay, let's start with p sub 1. Since p sub 1 divides n, that's the first expression. It means it therefore divides the product of the qi's. And by our earlier result, since p is prime, it has to divide one of the actual q sub i's. So up to reordering, we might as well assume it divides, or up to relabeling, we might as well assume p1 divides q1. But both p and q are prime, so if, and bigger than 0, so if p divides q1, then that's because they're the same. Okay, now we're going to divide out by p sub 1 on both sides, and we get this. All right, divide p1 on both sides, you get this. We've pulled out the I equals to 1 term and written it separately on both sides. Also remember, p1 is q1. I left it as q1 on the right, but they're the same. Now, the point is, this number here, which can be written in two ways as a product of primes possibly, has a lower s value. Okay, it's definitely lower by at least 1, and therefore, by our induction hypothesis, this expression is unique, which means all of these terms up to reordering are the same, with the same exponents. So that will finish up the proof. All the p's are q's after reordering and their exponents match. And that's it.